In this video, we will look at how to solve the multi-stage graph problem using backward approach of dynamic programming. In multi-stage graphs, the vertices of the graph are partitioned into k disjoint sets where k is greater than or equal to 2. The disjoint sets are represented by Vi where I range from 1 to k, and each disjoint set Vi defines a stage in the multi-stage graph. Therefore, in this example, we have 5 disjoint sets from V1 to V5. Furthermore, the first disjoint set is V1 and the last disjoint set is V5 and will contain only one vertex. The vertex in disjoint set V1 is represented by S and is known as a source vertex. The vertex in disjoint set Vk, or in this graph V5, is represented by T and is known as the sink vertex. The edges in the multi-stage graph are directed edges, and every edge will connect a vertex from one stage to another vertex of the next stage. So, if there is an edge between vertex u and vertex v, then vertex u belongs to disjoint set Vi and vertex v belongs to the disjoint set Vi plus 1. Then each edge has a cost. The cost of the edge between vertex I and vertex j is represented by C of I, j. Now the problem of multi-stage graph is to find a minimum cost path from source vertex S to sink vertex T using backward approach of dynamic program. So the dynamic approach formula using backward approach is represented by B cost of the path, where B stands for backward approach of I, j, where I is the stage and j is the vertex in that stage, equal to minimum of the sum of B cost of the path of the previous stage and every vertex in the previous stage plus the cost of the edge of every vertex L and vertex j, where L and j is an edge, and the cost of the path for every vertex j in stage 2 is the cost of the edge from source vertex 1 in stage 1 to every vertex in stage 2, that is C of 1, j, where j is the vertex in stage 2. Remember, B cost is the cost of the path and C is the cost of the edge. So, to start with, we have to compute the B cost of the path from stage 2 and every vertex in stage 2. So, the B cost of stage 2 and vertex 2 is B cost 2, 2, which is equal to the cost of the edge between source vertex 1 and vertex 2, that is C of 1, 2 and is equal to 9. Then B cost of stage 2 and vertex 3 is B cost of 2, 3, which is equal to the cost of the edge between source vertex 1 and vertex 3, that is C of 1, 3 and is equal to 7. Then B cost of stage 2 and vertex 4 is B cost of 2, 4, which is equal to the cost of the edge between source vertex 1 and vertex 4, that is C of 1, 4 and is equal to 3. And the B cost of stage 2 and vertex 5 is B cost of 2, 5, which is equal to the cost of the edge between source vertex 1 and vertex 5, that is C of 1, 5 and is equal to 2. So, we have computed the B cost of the path of all the vertices in stage 2. Now, we have to compute the cost of the path from all the vertices in stage 3. So, we have to compute the cost of the path from stage 3 and vertex 6, which is B cost of 3, 6, since I is the stage, which is 3, and j is the vertex in that stage, which is 6, and is equal to minimum of B cost of 2, which is the previous stage, and vertex 2 plus the cost of the edge from vertex 2 and vertex 6, and B cost of 2, which is previous stage, and vertex 3 plus cost of the edge from vertex 3 and vertex 6. So, the B cost of stage 3 and vertex 6 is equal to the minimum of B cost of 2, 2, which is 9, plus the cost of the edge 2, 6, which is 4, and the B cost of 2, 3, which is 7, plus the cost of the edge 3, 6, which is 2. So 9 plus 4 is 13 and 7 plus 2 is 9. So 9 is the minimum cost which is through vertex 3. Therefore, we will save the decisions made at each step in D of I, j, where I is the stage and j is the vertex, which is equal to L, that is the vertex that minimizes the B cost of I, j. So, since the minimum cost of the path from stage 3 and vertex 6 is 9 through vertex 3, therefore, D of 3, 6, where 3 is the stage and 6 is the vertex, will be vertex 3 that minimizes the B cost 3, 6. Then we have to compute the cost of the path from stage 3 and vertex 7, which is the B cost of 3, 7, since I is the stage, which is 3, and j is the vertex in that stage, which is 7, and is equal to minimum of B cost of 2, which is the previous stage, and vertex 2 plus cost of the edge from vertex 2 and vertex 7. Then B cost of 2, which is the previous stage, and vertex 3 plus cost of the edge from vertex 3 and vertex 7. And B cost of 2, which is previous stage, and vertex 5 plus cost of the edge from vertex 5 and vertex 7. So, the B cost of stage 3 and vertex 7 is equal to the minimum of B cost of 2, 2, which is 9, plus the cost of the edge 2, 7, which is 2. And the B cost of 2, 3, which is 7, plus the cost of the edge 3, 7, which is 7. And the B cost of 2, 5, which is 2, plus the cost of the edge 5, 7, which is 11. So, 9 plus 2 is 11, 7 plus 7 is 14, and 2 plus 11 is 13. So, 11 is the minimum cost which is through vertex 2. Therefore, D of 3, 7, where 3 is the stage and 7 is the vertex, will be vertex 2 that minimizes the B cost 3, 7. Then, we have to compute the cost of the path from stage 3 and vertex 8, which is the B cost of 3, 8, since I is the stage, which is 3, and j is the vertex in that stage, which is 8, and is equal to minimum of B cost of 2, which is the previous stage, and vertex 2 plus the cost of the edge from vertex 2 and vertex 8. Then the B cost of 2, which is the previous stage, and vertex 4 plus the cost of the edge from vertex 4 and vertex 8. And B cost of 2, which is the previous stage, and vertex 5 plus cost of the edge from vertex 5 and vertex 8. So, the B cost of stage 3 and vertex 8 is equal to the minimum of B cost of 2, 2, which is 9, plus the cost of the edge 2, 8, which is 1, and the B cost of 2, 4, which is 3, plus the cost of the edge 4, 8, which is 11, and the B cost of 2, 5, which is 2, plus the cost of the edge 5, 8, which is 8. So, 9 plus 1 is 10, 3 plus 11 is 14, and 2 plus 8 is 10. So, 10 is the minimum cost which is through vertex 2 and 5. Therefore, D of 3, 8, where 3 is the stage and 8 is the vertex, will be vertex 2 and 5. That minimizes the B cost of 3, 8. So, we have computed the B cost of the path of all the vertices in stage 3. Now, we have to compute the B cost of the path from all the vertices in stage 4. So, we have to compute the B cost of the path from stage 4 and vertex 9, which is B cost of 4, 9, since I is the stage, which is 4, and j is the vertex in that stage, which is 9, and is equal to minimum of B cost of 3, which is previous stage, and vertex 6 plus cost of the edge from vertex 6 and vertex 9, and B cost of 3, which is the previous stage, and vertex 7 plus the cost of the edge from vertex 7 and vertex 9. So, the B cost of stage 4 and vertex 9 is equal to minimum of B cost of 3, 6, which is 9, plus the cost of the edge 6, 9, which is 6, and the B cost of 3, 7, which is 11, plus the cost of the edge 7, 9, which is 4. So, 9 plus 6 is 15 and 11 plus 4 is 15. So, 15 is the minimum cost which is through vertex 6 and 7. Therefore, D of 4, 9, where 4 is the stage and 9 is the vertex, will be vertex 6 and 7 that minimizes the B cost 4, 9. Then we have to compute the cost of the path from stage 4 and vertex 10, which is the b cost of 4 comma 10, since I is the stage, which is 4, and j is the vertex in that stage, which is 10, and is equal to minimum of b cost of 3, which is previous stage, and vertex 6 plus the cost of the edge from vertex 6 and vertex 10. Then the b cost of 3, which is previous stage, and vertex 7 plus cost of the edge from vertex 7 and vertex 10, and b cost of 3, which is previous stage, and vertex 8 plus cost of the edge from vertex 8 and vertex 10. So the b cost of stage 4 and vertex 10 is equal to the minimum of b cost 3 comma 6, which is 9, plus the cost of the edge 6 comma 10, which is 5, and the b cost of 3 comma 7, which is 11, plus the cost of the edge 7 and 10, which is 3, and the b cost of 3 comma 8, which is 10, plus the cost of the edge 8 comma 10, which is 5. So 9 plus 5 is 14, and 11 plus 3 is 14, and 10 plus 5 is 15. So 14 is the minimum cost, which is through vertex 6 and 7. Therefore, d of 4 comma 10, where 4 is the stage and 10 is the vertex, will be vertex 6 and 7. That minimizes the b cost 4 comma 10. Then we have to compute the cost of the path from stage 4 and vertex 11, which is the b cost of 4 comma 11, since I is the stage, which is 4, and j is the vertex in that stage, which is 11, and is equal to minimum of the b cost of 3, which is previous stage, and vertex 8 plus the cost of the edge from vertex 8 and vertex 11. So the b cost of stage 4 and vertex 11 is equal to minimum of b cost 3 comma 8, which is 10, plus the cost of the edge 8 comma 11, which is 6. So 10 plus 6 is 16, and is minimum cost, which is through vertex 8. Therefore, d of 4 comma 11, where 4 is the stage and 11 is the vertex, will be vertex 8. That minimizes the cost 4 comma 11. So we have computed the b cost of the path of all the vertices in stage 4. Now we have to compute the cost of the path from vertex in stage 5. So we have to compute the cost of the path from stage 5 and vertex 12, which is b cost of 5 comma 12, since I is the stage, which is 5, and j is the vertex in that stage, which is 12, and is equal to minimum of the b cost of 4, which is previous stage, and vertex 9 plus the cost of the edge from vertex 9 to vertex 12. Then b cost of 4, which is previous stage, and vertex 10 plus cost of the edge from vertex 10 and vertex 12. And b cost of 4, which is the previous stage, and vertex 11 plus cost of this edge from vertex 11 and vertex 12. So the b cost of stage 5 and vertex 12 is equal to minimum of b cost of 4 comma 9, which is 15, plus the cost of the edge 9 comma 12, which is 4, and the b cost of 4 comma 10, which is 14, plus the cost of the edge 10 comma 12, which is 2, and the b cost 4 comma 11, which is 16, plus the cost of the edge 11 comma 12, which is 5. So 15 plus 4 is 19, and 14 plus 2 is 16, and 16 plus 5 is 21. So 16 is the minimum cost, which is through vertex 10. Therefore, d of 5 comma 12, where 5 is the stage and 12 is the vertex, will be vertex 10. That minimizes the b cost 5 comma 12. So this is how the cost of the path of the vertex in stage 5 is computed. Now after computing the cost of the path till stage 5, where we have sink vertex, we have the minimum cost of the path from source vertex 1 to sink vertex 12, which is 16, and the path is stored in the decision d, which is easy to trace. That is, d of 5 comma 12 is vertex 10. That means from stage 5 and vertex 12, the minimum cost path is from vertex 10 to vertex 12. Then from stage 4 and vertex 10, that is d of 4 comma 10 has vertex 6 and 7. So minimum cost path is from vertex 6 or vertex 7. Let us first choose vertex 6. Then from stage 3 and vertex 6, that is d of 3, 6 has vertex 3. So minimum cost path is from vertex 3 to vertex 6. Then to vertex 3 we have the minimum cost path from source vertex 1. So the minimum cost path from source S, that is vertex 1, to sink T, that is vertex 12, is from vertex 1 to vertex 3 to vertex 6 to vertex 10 and to vertex 12, and this minimum cost path is 16. We also have another minimum cost path, that is d of 4, 10 is vertex 6 and vertex 7. Let us choose vertex 7. Then from stage 3 and vertex 7, that is d of 3, 7 has vertex 2. So minimum cost path is from vertex 2 to vertex 7. Then to vertex 2, we have minimum cost path from source vertex 1. So the minimum cost path from source S, that is vertex 1, to sink T, that is vertex 12, is from vertex 1 to vertex 2 to vertex 7 to vertex 10 to vertex 12. And the minimum cost of this path is 16. So this is how we can use the dynamic programming approach to compute the minimum cost path of the multistage graph using the backward approach. Now let us look at the algorithm for solving multistage graph using backward approach. Let us call this algorithm as BGraph because it uses backward approach to make sequence of decisions. This algorithm has 4 parameters. The first parameter is graph G with set of vertices V and edges E. The second parameter is K, which is the stages of the multistage graph. The third parameter is the number of vertices in the multistage graph, and the fourth parameter is the array P, which will be storing the vertices of the minimum cost path once the algorithm completes its execution. Then the first statement is to assign B cost of the nth vertex or the last vertex as 0 in the B cost array. Then we will have a for loop for j 2 to n. This for loop is used to compute the B cost and decisions starting from the second stage. That is why the for loop starts from 2 and ends at n. Then we choose each vertex r such that there is an edge in the graph from vertex r to vertex j, and the sum of the B cost of the path r and the cost of the edge between r and j is minimum. Then we update the B cost of the vertex j using the dynamic programming formula for backward approach. B cost of j assigned B cost of r plus the cost of the edge between vertex r and vertex j. Then store the decision of vertex j assigned vertex r since it leads to the minimum cost. Now once the for loop computes the cost of the vertices in each stage and terminates, then we will have the minimum cost stored in B cost array, and the path from source vertex to the sink vertex is stored in the decision array D. Then we have to determine the path. So we have path array P of 1 assigned vertex 1, which is the source vertex, and in the next statement we have the path P of k assigned n, which is the sink vertex. Now remember that at each stage we will have only one vertex in the path. Then to determine the vertices of the path along the stages, we will use a for loop for j equal to k minus 1 to 2. Here we are determining the vertices from the last but one stage to the second stage. So we have the for loop from k minus 1 to 2. Then within this for loop, the values from the decision array at indices corresponding to the minimum cost path are assigned to the array P using the statement P of j assigned D of P of j plus 1. So this BGraph algorithm computes the minimum cost from source vertex to sink vertex in the multistage graph using the backward approach of dynamic programming, and the path is stored in the path array P. Now let us analyze the complexity of this algorithm. The first statement is the primitive statement. Then we have a for loop which will execute for n times, where n is the number of vertices. Then the statement to choose a vertex r within the for loop will execute for e times, where e is the number of edges. But if the adjacency list is used to represent the graph, then the for loop will be taking theta of v plus e times. Then we have another for loop to find the minimum cost path, and this for loop will be taking k times to execute, where k is the stage of the multistage graph. Therefore, the overall complexity of this algorithm is theta of v plus e. So this is all about the multistage graph and how the minimum cost and its path is computed from source vertex to the sink vertex, as well as the algorithm for solving the problem using backward approach of dynamic programming and its time complexity.